My name is Paul Holler, and I'm a product manager here at PROS.
Hello, my name is Ravi Kumar, and I'm a lead scientist at PROS.
And today we're going to be talking to you about dynamic pricing. It's alive. In today's presentation, we'll be covering three major topics. First, we'll be talking about the different types of dynamic pricing as seen by PROS. Secondly, we'll demonstrate how airlines can get involved with PROS to realize that the capabilities of dynamic pricing. And third, we'll take a deeper look into the willingness to pay forecasting, which is a key component of the dynamic pricing algorithms. So here at PROS, we think that there are three different types of dynamic pricing. Each of these is geared towards a specific use case for airlines and trying to meet the needs of the marketplace associated with different levels of sophistication of both airlines as well as the algorithms behind this. These different types of models, types of dynamic pricing include assortment optimization, price adjustments, and continuous pricing. Assortment optimization is the idea that you have a set of booking classes, each with a fixed price associated with it. The optimization process opens and closes classes based upon demand to come forecasts. In this situation, M and Q class are closed, while Y and B class is available or open. In this situation, the offered price is the price associated with the lowest open class, in this case B, or $500. This becomes dynamic because the classes which are open and closed change with time based upon the seats remaining and the time to departure. Price adjustments takes this one step further by allowing airlines to price in between those filed prices. So in this situation, you still have booking classes, each with a particular fixed price associated with it, but the dynamic pricing algorithms determine an adjustment factor that should be applied to those prices to get to that final price. In this case, B class is still the lowest open class, but the dynamic pricing engine has determined that there should be a 10% discount associated with the price so that the offered price becomes $450. Lastly is continuous pricing. Here we have moved away from the booking classes and we forecast demand as a function of price and as a continuous curve at that. Therefore, the optimization process uses that continuous nature of the curve to generate what the optimal price should be. In this case, $460. The pros that we see that there are many different uses for these different types of dynamic pricing, and that there can be a progression that airlines can take on it. Here we show the different products and functionality that an airline can enable so that they can realize different stages of and different types of dynamic pricing. This starts off with our core RM product of RM Advantage. It extends into the willingness to pay, which is a new forecasting and optimization process, and that enhances the capabilities of the RM Advantage edition. This is then carried on into RTDP Ultimate, which provides a dynamic pricing functionality associated with the price adjustments. Lastly, we can look into the future directions where we look towards the RM Ultimate edition of the RM product to incorporate continuous pricing functionality. Let's look into a little bit more detail in each of these areas. All of dynamic pricing here starts off with our core RM Advantage product. This is our foundational product, which has been in the marketplace for a while and been used by a number of airlines of a variety of shapes and sizes around the world. And so it has a strong history of being robust, robust functionality. This is a cloud-based RM O&D product. It has a traditional forecasting, which uses Bayesian models, so it can update and learn based upon new observations, based upon a yield-able model. Optimization includes a network optimization, so it incorporates that O&D behavior in terms of the optimization process, and then calculates the optimal controls based upon that. One issue with it can be with the traditional model is that it has a yield. The forecasting assumes a yield-based passenger content. However, passengers tend to be also not only be product sensitive, but they can be price sensitive. So in this case, if you have two booking classes, they tend to buy that lowest product that's available, which is going to dilute yield, even if they might have a higher willingness to pay. To prevent this, airlines must implement manual controls, force that buy up to those higher yield classes. However, wouldn't it be nice to have some kind of RM system that handles this automatically? This can also be done more scientifically so that as today's controls tend to be based upon load factor or advanced purchase restrictions. This is where willingness to pay comes in. Again, this is a new forecasting and optimization process which incorporates the price-sensitive behavior into that forecasting procedure. So it estimates and forecasts a demand price curve, and so that the correlation between the different demand at different price points is baked into that process. The forecasting itself doesn't rely on the booking classes, and it uses the price information, but we still discretize it down to the class level so that the analysts can still manage it at that level so that it's easier to use or more consistent with what they're working with today. From the studies that we've done, we've seen that this also improves forecast accuracy. In terms of optimization, we use the concept of transform fares. This captures the true value of a booking class, considering that priceable or buy down potential of the passengers. And because of that, we see that this generates better bid prices, which also automatically drives those passengers to those higher valued booking classes. We've seen that this enhances revenues from RMA by 1 to 2%. And this was released earlier this year as part of the 548 release of the RMA edition. However, to support this further, we've also introduced new screens into the RMA product, such as this one, which showcases demand as a function of price. This will help analysts see these curves better and get used to managing these continuous price situations. However, this might not be sufficiently enough, that you might need some more price points into the marketplace. And that's where the price adjustment situation comes in. So for example, even in the case of 2 price points, if I price too low, that might not I might stimulate too much demand, and so my yield gets diluted. However, if my only other option is class Y here, that might be too high, and so that my demand then becomes stifled. So that though I'm generating more revenue per passenger, I'm just not getting as much revenue because of the number of passengers that I take in. And so therefore, we want to identify this sort of just right price that would fall in between these, which would optimize the profit. And so being able to do this gives airlines the ability to price in between the points to realize more revenue opportunities, and it gives pricing controls back to the airlines. The pros that we realize this through our RTDP Ultimate product. This includes a scientific algorithm to price in between those booking class fares. There are 3 major inputs into that algorithm. First, the fares by class. This captures the potential prices in the marketplace, so we know what fares that are there to provide the adjustments accordingly. Bid prices, which captures the capacity constraints, very much in the same way as it does today with traditional forecasting and availability. And thirdly is the transform fares, which again captures the buy down potential. One key source of this would be willingness to pay forecasting, which provides an enhanced version of those transform fares, and therefore further enhances the dynamic pricing capabilities. We estimate a revenue benefit between 1 and 1.5% over RMA with willingness to pay. And this is included in the product today. So airlines can implement this with their systems today. In terms of future directions, we want to enhance the willingness to pay forecasting and optimization process. Ravi is going to talk about one way we're looking to further enhance this, which is the using of competitive fares. But also we look forward in terms of our RM Ultimate Edition, where we go fully towards that continuous pricing model with class-free revenue management and incorporating the willingness to pay models into the dynamic pricing decision itself. As well as providing even more granularity to the pricing decisions with some customer-specific pricing, and allowing airlines to tailor more of that pricing aspects at the time of request. So at this point, I'm going to turn it over to Ravi to go into a little bit more details on the willingness to pay model, again, a key component into the dynamic pricing models. So Ravi, take it away.
Thanks, Paul. So I'm going to dig deeper and go into further details of one of the key drivers for dynamic pricing, which is the willingness to pay forecaster. So the willingness to pay forecaster is a new type of forecaster for priceable demand situations. The main idea here is that we model demand for a differentiated product, which could be a fare family, a class block, or the entire compartment using price demand response curves. Here is an example of a price demand response curve where on the X or horizontal axis, you have the price, and on Y or vertical axis, you have the demand. This price versus demand relationship is captured using this negative exponential relationship. And it is there are two parameters which control this curve. One is denoted by lambda. So this, in some sense, is the total amount of expected demand that you will get if you price at a fairly low level of price, in this case, a value called P naught. And alpha controls the price sensitivity of the consumer population. So higher value of alpha means that this is a flatter curve, and lower value of alpha means it's a steeper curve, and the demand is quite responsive to prices. So therefore, the main function for a willingness to pay forecaster is to figure out these demand response curve parameter values for lambda and alpha for future departure dates. So let's go deeper into how that is done. Uh, the willingness to pay forecaster is a configuration of our Bayesian model. And therefore, all the good functionalities that you associate with the Bayesian model for our traditional forecaster naturally extend to this forecaster as well. In particular, it means that we organize the data into data guillotines, and therefore we can make much more dynamic updates to our forecaster by making use of partially completed departure dates. Furthermore, we also model non-stationarity in the arrival process or the demand process using drift, as well as we make use of correlation across DCPs to update the forecast much more dynamically. And naturally, there is seasonality and holiday and special events which are built into this forecaster as well. So for this, however, for this forecaster, in addition to the bookings, another piece of information that we take is the average offered price paid for that product in a particular period of time. So that's a new kind of input that this forecaster uses. But however, once you have this historical booking and price information, what we do is we apply a methodology called online variational base, which is a machine learning technique to come up with uncensored demand estimates or parameter estimates for our demand response model. These are these alpha and lambda values for the historical period. So once you have for the historical period your demand model parameters, we then feed them into our Bayesian dynamic linear model, which then produces forecasts of time series for each of these parameter values, both alpha and lambda. So now you have the output of these demand model parameters for future forecasted date, and these can then be consumed by your optimization algorithm. For RMA, which works at class level, these price demand response curves are discretized using daily fares to get class level demands. Whereas for RMU, it has the capability of consuming price demand response curve on a continuum level. We have done extensive amount of testing, both on simulation test bed, as well as with real data set to verify that the willingness to pay forecaster works well. So in particular, on simulation test bed, we have done testing to figure out the robustness of this forecaster. So one question is that if the forecaster starts with parameters which are quite off, then as it gets more data over forecast and optimized cycles, does it recover the true parameter values? So one such test in this picture on the left, we are showing you how the parameter values, in this particular case, the alpha parameter value, which starts off with around 50% error, as it gets more data, you see it quickly converges to the true value, which is denoted by the flat green line. So within 50 or so cycles, it is fairly close to the true parameter values. You can see this effect when you are looking at the revenue produced by the system as well. So at the start, when the parameter values were quite off, your revenue produced by the system is naturally far away from the true optimal. But as the system is learning fairly quickly, it converges to true optimal values within 50 iterations or so. So this shows that this forecaster is robust, and it picks up the price and what is the right price sensitivity even when the starting values are off. In addition to such simulation studies, we have done extensive amount of POCs with real airline data. In particular, so far we have done around testing with around 10 airline data sets. And we have seen very robust performance in terms of patterns that the forecaster captures. So this is one example where in the high demand period, the top panel is showing you the red dots are the bookings. The blue curve is this unconstrained lambda or the volume value. And in the bottom panel, the blue curve is the price sensitivity parameter alpha. So in the high demand period, we see that both the lambda value increases as well as the alpha value or the price sensitivity increases. That means that people are willing to pay a bit more during the high demand period. And these trends, which were captured through historical uncensoring, are then projected into future, and these trends are shown in the future forecast period as well. So we have seen very robust performance when it comes to capturing trends and seasonal patterns. But in addition to the qualitative patterns, we have done extensive amount of quantitative testing. So we have done a recent study, a large scale study with a large network carrier, where we tested the willingness to pay forecaster over 150 markets. And this forecaster showed around 10% improvement in forecast accuracy when we used root mean squared error or mean absolute deviation as metrics. Over the past year or so, we have done extensive work on incorporating third-party or non-traditional data to the willingness to pay forecaster, and thereby improve the forecast accuracy. One particular area where we have put a lot of emphasis on is how to incorporate competitor fares into willingness to pay forecasting. So in past few months or so, we have developed a couple of demand response models, which actually can take competitor price as a covariate and can produce demand response curves which are sensitive to that competitive fare. So both the price sensitivity and other parameters are affected with based on what the competitive price is. Now, having these kind of competitive price aware forecasts allows you to build strategies which tell you based on the competitor price whether you should match or ignore the competitor. And if you decide to ignore the competitor, what is the right amount of competitor aware margin that you should be charging. So all of this is into well advanced research. And we have also tested these competitor aware willingness to pay model using real airline data set using based on one of our airline partners. And we saw an increased efficiency and improved performance of accuracy of about 5 to 10% over willingness to pay forecasts, which do not consume or do not take into consideration competitor prices. We have also written a paper which details both methodology and some of these tests. And this paper is submitted and accepted at JRPM special issue on artificial intelligence and machine learning in travel. It hasn't appeared online yet, but if you are interested in finding more details, then please send us an email or contact someone in our booth, and we will happy to share an advanced copy of the paper with you.
So thank you very much, Ravi. In conclusion, we've introduced and shown you how the world of dynamic pricing is here with pros. We've also laid out a plan on how airlines can start using dynamic pricing even today. And a key first step of this is to start using the new willingness to pay forecasting and optimization process. Ravi's also shown us a deeper look into the methods behind willingness to pay and shown us some of the technical enhancements thereof. So thank you very much for your time today. If you have any questions, you feel free to contact either Ravi or myself, or you can head on over to the innovation booth sometime during Outperform. Otherwise, thank you very much and have a great rest of your day.